Okay, let us start today's session. So, welcome everyone to the second problem solving session for a deep learning course on noc23 sessions. So, today we will mainly talk on discriminant functions, perceptron criteria, decision surfaces for discriminant functions, things like that. So, let us get started with the first problem. So, the first problem we have today is if I choose the discriminant function gix as a function of posterior probability, that is gix is some function f of the probability of omega I given x, then which of the given functions, four options are given in ABCD, which of them cannot be the function f which is suitable for a discriminant function. So, you have four options, one is a to the power x where a is greater than 1, another is a to the power minus x with a greater than 1, then 2x plus 3 and exponential of 3. Can anyone give this answer? So, which function is not suitable for being the function f? Manoj is saying option C. Mani is also saying option C. Can you tell me the reason? You can unmute and speak up. One of you, Manoj or Mani, please, if you can give me the reason why you think C cannot be the function f.
Hello, madam.
Yeah.
Mani here.
Yeah.
Because posterior probability means we need to know the prior information of that. So this doesn't have any such kind of thing. So I think it is
Any such kind of things in the sense? Here, yeah, tell me.
To find out the posterior answer, to find out the posterior probability, we need to know the prior information. We need to have the prior information about it.
Okay, here we are not concerned about how this posterior probability will be computed. You assume you have somehow you have computed the posterior probability and you want a function of that posterior as your discriminant function.
Yes.
No need to bother about the how you will get the posterior probability. So, let us say the prior information is given to you. You have all the necessary information for computing p of omega I given x. In that case, what will be what function you cannot choose? Okay, so three answers I got, all are C only, but no, C is not the correct answer. So, the only criteria you have for this f function is it has to be monotonically increasing. So, you can choose any function, you can take any function of the posterior probability as long as it is a monotonically increasing function, because so when we do this discriminant function based classification, what is the idea? The idea is that for each class you have a discriminant function. You compute the value of the discriminant function for each class when you are given a unknown sample. Now, whichever class has the highest value of this discriminant function, we will classify the unknown sample to that particular class. Now, when we use the Bayes minimum error criteria, we see that we can just take this posterior probability, and whichever class has the highest posterior probability, we can assign the test sample to that particular class. So, only taking this posterior probability itself, you can take that as the discriminant function. So, for whichever class has higher posterior probability, you assign to that class. Now, if you want to take a function of this posterior probability, this is mainly done for computational convenience. So, you have to have a monotonically increasing function. So that whenever you have higher posterior probability, you will also get higher value of this overall discriminant function. So, in case of 2x plus 3, which is option C, that is absolutely valid. The class which will have the highest posterior probability, that class only will have the highest value of the discriminant function. So, you can easily take that and classify into the class having the highest posterior probability. But only if the function is monotonically, only if the function is not monotonically increasing. In that case, it might happen that some class has higher posterior probability, but you are getting lower discriminant function value for that if the function is not monotonically increasing. So, that kind of function you cannot choose. So, only such function present in these options is a to the power minus x, which is not a monotonically increasing function, it is actually a decreasing function given a greater than 1. So, only option B you cannot use as the function here. So, the correct answer in this case will be option B. Option B cannot be a discriminant function in this scenario. So, is it clear to you guys, Mani, Manoj, Safiq? Yeah, okay. So, just you have to check only one thing, that your function should be monotonically increasing. You can select that function. For example, you can take log, you can take exponential, any linear function you can take. Similarly, a to the power x also you can take as long as a is greater than 1. Okay. Now, given that, let us take one example and try to compute these discriminant functions and decision boundaries and try to classify some unknown example. So, here in this problem, there are two classes, omega 1 and omega 2, and in both classes you have 4 samples known. So, this is basically your training data. All these 4 samples belong to class omega 1 and these 4 samples belong to class omega 2. So, the first part of this question says compute the mean vectors and covariance matrices of the 2 classes. So, this is very straightforward, I do not need to explain, I guess. So, first let us compute the mean vector. Can anyone compute the mean vector and tell us for both the classes? So, when you compute mean vector of 4 data points, is just element wise you will have to do the average. So, if we take class omega 1, we have 4 samples 1 1 2 0 2 2 3 1. We just need to take the average of this. So, for class omega 1 it will be 2 1, right. So, just we take the average of 3 2 2 1, the first elements, and that is 2, and we take the average of 1 0 2 1, which are the second elements, the average is 1. So, this is the mean vector for class omega 1. Similarly, for class omega 2, if you compute, the mean vector will be 8 1. You can verify later. Now, once you have the mean vectors, the next question is you will have to compute the covariance matrices of the 2 classes. So, what is the expression formula for computing covariance matrix? Let us say sigma is your covariance matrix. This is computed as expectation of x minus mu into x minus mu transpose. So, expectation of x minus mu, where mu is the mean of all the samples x, into x minus mu transpose, which will be a matrix. So, in this case it will be a true cross 2 matrix. So, we will compute for first, let us say class omega 1, I will compute it. So, for class omega 1, if I denote it by sigma 1, this will be expectation of x minus, okay, sorry, x minus mu 1 into x minus mu 1 transpose, where our mu 1 is 2 1. Now, since we have a limited number of samples, only 4 samples, we have to approximate the expectation by average. So, what we will do is, we will replace the expectation by the population mean. Here I am taking N1 as the number of samples present in the first class omega 1, which in this case is 4, because we had 4 samples. So, the formula will be like this. So, 1 by N1 summation of overall I xi minus mu 1 into xi minus mu 1 transpose. So, we can simply compute it in detail for one of the classes. Let us say, so the first data point in class omega 1 is 1 1 1 1. If you subtract the mean out of it, it becomes minus 1 0. Now, if you do minus 1 0 into minus 1 0 transpose, what we will get is 1 0 0 0. Similarly, the next sample we have is 2 0. So, here we will get, after subtracting mean, we will get 0 minus 1. Now, you have to do 0 minus 1 into 0 minus 1 transpose. So, you will get 0 0 0 1. Third sample is 2 2. So, again after mean subtraction we get 0 1, and xi minus mu 1 into xi minus mu 1 transpose will be 0 0 0 1, and the last sample is 3 1. After subtracting we get 1 0, and this will become 1 0 0 1. So, now as per this formula, you just need to sum up all these 4 matrices that we got here, and we need to divide it by n1, which is 4. So, if you do that, you will get final sigma 1 as 1 by 4 into, here you have 2 0 0 2. Okay. So, basically half I, where I is the identity matrix. So, this will be the covariance matrix for the first class. This way you can compute the covariance matrix for the second class as well. Only a small change in the formula will happen. This will be 1 by n2. I will be summed from 1 to n2, xi minus mu 2 into xi minus mu 2 square. So, what we will have to do is, you will take each sample from the other class, subtract the mean of that class from the sample, and compute this xi minus mu 2 into xi minus mu 2 transpose. You take the sum, divide by the number of elements. If you complete this process for the other class, where your samples are the 6 1, 8 minus 1, 8 3, 10 1, and your mean vector is 8 1. So, finally, you will get sigma 2 as 2i, that is 2002. This will be the covariance matrix for class sigma 2. I hope the computation of covariance matrix for any class from a given number of observations is clear. If you have any doubts, you can at any point stop me and ask. Now the next part of the question was, assume that the classes are normally distributed and equiprobable. So the prior probability of both the classes are equal. Probability of omega 1 is equal to probability of omega 2. Let the discriminant function of a class be the logarithm of the posterior probability of that class. Now you have to determine the decision boundary. So first let us determine the discriminant function for the classes, then we will go for the decision boundary. So here it is mentioned that the discriminant function will be the logarithm of the posterior probability of that particular class. So for any class I, for the ith class, let us say, I denote the discriminant function by gix. So gix will be, as per the problem, probability of log of probability of omega I given x. So the posterior probability of class omega I, that is probability of omega I given x, we take the logarithm of that as the discriminant function. So here this posterior probability information is not known, as Mani was saying in the previous first problem, that posterior probability we need the prior information. So here it is said that both the classes are equally probable. So we know that the prior probability is half, and we have been given the class conditional density, which is, it is said that the classes are normally distributed. So we know both those information. We can simply use that information here, and using Bayes rule, as we did in our last session also, we can just write it like this. If you further simplify this, this becomes p of x given omega I plus ln of p of omega I minus ln of p of x. So this is basically the discriminant function for ith class. Now the question for us is, we need to compute the decision boundary. So we know that here it is a two class problem, class omega 1 and omega 2, two classes are there, and we know that at the decision boundary the condition is the discriminant function value for both the classes will be equal. So g1x minus g1x will be equal to g2x at the decision boundary. At the decision boundary, or you can say that g1x minus g2x will be 0, which is the equation for the decision surface. So here we can just compute g1x minus g2x for our example. So we want to compute g1x minus g2x, and we already know the expression for gix. We will put that. Plus ln of probability of class omega 1 minus ln of probability of x minus g2 will be ln of probability of x given omega 2 minus ln of probability of prior probability of omega 2 plus ln of p of x. Now here ln of p of x is same for both g1x and g2x, so this term simply cancels out. We are also we know that the two classes are equiprobable, that is probability of omega 1 is equal to probability of omega 2, so these terms also cancel out. So finally we are just left with ln of probability of x given omega 1 minus ln of probability of x given omega 2. Now the question said that these class conditional densities are basically normal densities, and this is a 2D feature vectors are there. So this will be a 2D Gaussian distribution. So the expression for 2D Gaussian distribution with mean mu and covariance matrix sigma is, all of us know. We will just put mu1 for class omega 1 and mu2 for class omega 2 as the mean, and sigma 1 and sigma 2 for the covariances. So we can just write this as ln of 1 by 2 pi to the power d by 2 is the formula. Here d is equal to 2, it is 2D feature vectors, so it will be only 2 pi, determinant of sigma 1 to the power half exponential of minus half x minus mu 1 transpose sigma 1 inverse x minus mu 1. This is the, we are just using the general expression for multivariate Gaussian distribution, minus ln of 1 by 2 pi determinant of sigma 2 to the power half exponential of minus half x minus mu 2 transpose sigma 2 inverse x minus mu 2. Now we have to simplify this. So I'll do a bit of simplification on this. So what we will get is minus ln of 2 pi minus half ln of sigma 1 determinant minus half x minus mu 1 transpose sigma 1 inverse x minus mu 1 minus ln of 2 pi So this is what you get. Now you have to simply, so this 2 pi ln 2 pi terms cancels. Other than that we have to put, so we've already calculated the value of mu 1 as 2.1, mu 2 as 8.1, and we have also computed sigma 1 and sigma 2. We will just have to compute the inverse of those and determinant of those. So if you put all those values, I am not doing the detailed simplification for this. If you put all those values, finally the expression that we will get is something like this. So here I am assuming that we are using this variable x for our feature vectors, right? I assume that the definition of x is like this. The first dimension I call as x1, second as x2. So if you put like that and simplify the entire thing, finally you will get this. Minus 0.75 x1 square minus 0.75 x2 square plus 1.5 x2 plus 12.64. Something like this you will get for g1 x minus g2x. So this is g1x minus g2x. So if you want the expression of your decision surface, that will be simply this equals to 0, that is this. This is your decision surface. Now you can simply check this derivation whether you have computed it correct or wrong. So this is your decision surface. If you take this expression for you computed this as g1x minus g2x. So if you have the value positive for this term, then g1x minus g2x is positive. So your g1x is higher. So the sample should be from class 1. So if you just put a training sample in this, let's say we take the training sample 20 from the first class, this one 20, and we put it here. So our sample I am taking is x equal to 20. So if you simply put that here, you get minus 0.5 into 4, x2 is 0, 0 plus 12.64, which is, as you can see, greater than 0. So it belongs to class omega 1. So we generally say g1 minus x, g1x minus g2x equal to 0 is the decision boundary. If it is greater than 0, your class is omega 1, and if it is less than 0, your class is omega 2. So with one of the training samples, you can simply check whether that condition is satisfying. So I took this sample from class omega 1 and I computed the g1x minus g2x as per our expression, and I am getting positive. So indeed this is the decision boundary, and this sample 20 according to this boundary also belongs to class omega 1. Similarly, you can check with one example from the other set also. So this is how you compute the expression for the decision surface or decision boundary, whatever it's. Yeah, so in this case it won't be decision surface, since it's 2D, this will be decision boundary. Now let us move on to the last part of this problem. The last part was classify an unknown feature vector x 4.51. Can anyone tell me which class this 4.51 will belong to? So what will be the process to compute that? Again, you take this expression for the decision surface, this one, decision boundary. This is g1x minus g2x. You put your value here, you obtain the, you simplify the value, and what you get, if that is positive, your sample belongs to class omega 1. If that is negative, your sample belongs to class omega 2, because if this one is positive, then g1 minus x is positive, that is g1 is greater than g2x. So if you so what you have to do is, the unknown sample is 4.51, so your x1 is 4.5 and your x2 is 1. You can simply put those in this expression and compute whether this is greater than 0 or less than 0. If anyone can help with the calculation and let us know whether it is positive or negative. Yeah, Sunidhi is saying this is negative. Yeah, it's supposed to be somewhere near minus 1.8, I guess. So if it is coming as negative, so we will, so 4.51, for this you are getting g1x minus g2x less than 0. So your g2x is higher, so you will classify it to be from class omega 2. So this is how, given some data samples, and if you know the how the class conditional probability and the prior probabilities are, this is how you compute the discriminant functions. From that you compute the decision boundary or the decision surface, and depending on those equations you can classify any unknown feature vector into one of the two classes. Let us take one more similar example. So here the mean and variance of all the samples of two different normally distributed classes omega 1 and omega 2 are already given. So what we computed in the last problem, those informations are already here. So what we are supposed to do is, what will be the expression of decision boundary between these two classes if the both classes have equal prior probability. Here another information is given that for the input sample x, we have to consider gix as this expression. So, the discriminant function expression for class omega I is already given to you. You just need to compute g1x, you need to compute g2x. To compute g1x, you will simply use the values of omega 1 and sigma mu 1 and sigma 1, and to compute g2x, you will put the values mu 2 and g2, mu 2 and sigma 2. And once you have this g1 and g2, you can simply compute g1x minus g2x and finally make that equal to 0 to get the decision boundary expression. I have a few questions in the chat. When would the recording of all these live sessions be made available on the NPTEL course? Suresh Chandra sir, this I guess this should be available soon. I am not sure about the exact date, but yeah, we are already recording the sessions and we are giving the links, YouTube links of these sessions to NPTEL. They will publish it soon. Arun, is this session recorded and shared later? Sure, Arun, this session is being recorded. The links of these sessions you will find in the course web page in NPTEL. So, you I guess have a Excel sheet over there. You will, in that sheet you will get both the links of these recordings as well as the links for these PPT or whatever material we are using in these sessions. Okay. So, let us continue with this problem. So, I will not compute the entire thing because this is exactly same as the previous problem. Simply you compute g1x and g2x, and if you do that, finally what you will get, you should verify this anyway. So, g1x minus g2x you will get as this will be your expression for g1x minus g2x. So, this will be the so if you equate this to 0, this will be the equation for your decision boundary, or you can simplify this and write it like this. This will be the decision boundary. Now, you can use this g1x minus g2x expression and classify any unknown sample to one of the two classes. Moving on to the next question. Now, here it is said that the decision surface between two normally distributed classes omega 1 and omega 2 is shown in the figure. So, this is omega 1, this is omega 2 and this is omega 1. These two are the distributions of omega data points belonging to classes omega 1 and omega 2, and this is your decision surface. Now, you have to say which of the following is true, whether the class prior probabilities of the two classes are equal or one of them is higher, or if one of them is higher, which one is higher, or you can't say anything by just looking at this information. So, can anyone, what do you think will be the answer? Is the prior probabilities equal? Pooja is saying option C, which is probability of class omega 1 is greater than probability of class omega 2. Anyone else? Does everyone agree with this option? Okay, I don't see any objection, so I assume everyone is agreeing. Yeah, absolutely correct option, Pooja. So probability of omega 1 is greater than probability of omega 2. So how you can tell this is, if you have both classes equiprobable, then the decision surface should be midway between the two classes. It should be a bisector of the line joining the two means. But if your two classes are not equiprobable, then the decision surface will shift accordingly. As separation boundary towards W2, yeah, absolutely correct. So if you have higher probability of class omega 1, you should have more chance of classifying data points to class omega 1. So your decision boundary will be shifted towards omega 2. So more region are allotted towards class omega 1. Similarly, if your class omega 2 has higher prior probability, your decision surface will be shifted towards class omega 1. In this case, the decision surface is shifted towards class omega 2. So probability of omega 1 is higher than probability of omega 2. Yeah. Okay. Now let us see one more problem on decision surface. This is the last one, then we will move on to perceptron. So here it is said that this is also a two class problem, that the classes be omega 1, omega 2, and it has a d dimensional binary feature vector. So your feature vector x is d dimensional, that is x1, x2, like that you have till xd, and each of these xi can be either 0 or 1, because these are binary feature vectors. And ai is probability of xi being 1 given class is omega 1, and bi is probability of xi being 1 given class omega 2. Now you are given the information that assume all the features are statistically independent and the classes are equiprobable. Which of the following corresponds to equation of decision surface? So we know the process of computing this. So here also let's take gix as the discriminant function, and let's take that equal to log of the posterior probability. And like before, we can write this as right. So when we need to find the decision surface, so again we need to compute g1x minus g2x, which we can just write as ln of probability of x given omega 1 plus ln of probability of omega 1. This px will be cancelled from both sides, so I am not just writing that. This. Now you need expression for probability of x given omega 1 and probability of x given omega 2. So you need to know the class conditional densities. So here it is said that, so let's say we want to compute probability of x given omega 1. Okay. That PMF we want to compute. Now it's said that the features are statistically independent. So all your xi's which form the overall feature vector x, all those xi's are statistically independent. So you can simply break down P of probability of x given omega I as product of probability of xi given omega 1 for I equals to 1 to d, because these samples, these features are statistically independent. So their joint probability will just be the product of their individual probabilities. So you can simply write probability of x given omega 1 as the product of probability of xi given omega 1 over all I. Now, how will you write probability of xi given omega 1? So, you have been given the information that probability of xi equal to 1 given class omega 1 is given by a1. So, when your value of xi is 1, your probability is given by a1, ai, sorry, this is given by ai. And when the value of your xi can take only two values, 1 and 0. So, when it is 1, the probability is ai. So, when it is 0, the probability will be 1 minus ai. So, you can simply write this in a compact form as ai to the power xi into 1 minus ai to the power 1 minus xi, right. So, if you put xi equals to 1, your 1 minus xi becomes 0, the second term goes to 1, you just are left with ai. And when you have xi equals to 0, then this first term goes to 1 and you are left with 1 minus ai. So, this way you can write the PMF of this particular feature, the two classes, the class conditional densities. Now, simply we need to put this expression in our decision surface equation. So, this will become ln of I will write the other class conditional density just after this. Plus you have ln of p of omega 1 by p of omega 2. So, you can simplify this, product will become sum xi ln of ai plus 1 minus xi ln of 1 minus ai, this is the first term, minus again sum I equals to 1 to d xi ln of bi plus 1 minus xi ln of 1 minus bi, this is the second term, plus ln of p of omega 1 by p of omega 2. Can further simplify this to get to one of these given expressions, we need to further simplify this. So, what we get is you can take the xi terms together and take the 1 minus xi terms together So, this is the final expression for g1x minus g2x. You can simply equate this to 0 to get the decision boundary. Put it this way, this is under the summation. So, the options that you had, option B is one of the correct options. Another, you are given one more information here, that the classes are equiprobable. So, if classes are equiprobable, your probability of omega 1 is equal to probability of omega 2. So, the ln of this term is ln of 1, which goes to 0. So, it reduces to option A. So, both these options are actually signifying the equation of the decision surface in this particular example. I will take a 2-minute pause here. If you have any questions regarding this discriminant functions or decision boundaries, decision surfaces, you can ask that at this point. In the problem statement, it is given xi belongs to 1 or minus 1. Which problem are you referring to? This last one, the problem 5. Okay. Yes, Arun, the classes are equally probable. That's why I said both option A and B are correct. Yeah. So, probability of omega 1 is equal to probability of omega 2. So, these probability of omega 1, P of omega 1, P of omega 2, these are the class prior probabilities. So, your class, if your classes are equally probable, both these terms are equal. So, it simply cancels out and it becomes ln of 1 in this term. So, it just becomes 0 and your option A is also a valid option. Both of these are correct just because probability of omega 1 is equal to probability of omega 2. Okay, so let us move on to the next part of our problem solving session. Next, we will talk about perceptron criteria. So, in the class lectures, you have seen the perceptron algorithm, where the idea is that you have the data points, let's say x, from both classes. You want to determine a linear classifier, linear discriminant between the two, and so the form will be W transpose x plus W naught, where W is the weight vector, W naught is the bias term, and your x is the sample point. Now, to make it so, the bottom line linear classifier is basically of this form. This is equal to 0 will be your decision boundary. Now, to make it more computationally easier, we just append this W0 to the W vector, and we make it a augmented W, and also we append 1 at the end of the x vector, so that the overall expression remains this, but now we can write it as W transpose x. So, let me write this as W1, let's say. So now your W is basically W1 W0, and your X, let's say this was X1, X is basically X11. So this is we call what we call augmented feature vector. So you have this W transpose X equal to 0, that is your decision surface. When you have W transpose X greater than 0, then X, let's say element of class omega 1, and when it is less than 0, it is element of class omega 2. Now what we do is we take the x samples from class omega 2 and multiply those by minus 1. Now if you multiply those to minus 1, earlier this W transpose X was supposed to be less than 0. Now you have negated the X, so your W transpose X becomes greater than 0 for class class omega 2. So what we do is we just negate the samples of class omega 2. So that now all samples have the W transpose X greater than 0 whenever they are correctly classified. But here this X is negated for class omega 2. So this is the setting in this perceptron criteria setting. Now what you do is, for obtaining the weight, you start with some initial guess of W, let's say W0 as 0 maybe. Then you try to classify all the points using this W. So you compute W transpose X and you determine which one are correctly classified, which one are not. So you just check whether W transpose X is greater than 0, then it's fine, those elements are correctly classified. Otherwise those are some wrong classification is happening for them. So how do you update your weight vector? You do Wk plus 1 equal to Wk plus eta times summation of xk, let me write, for all xk which are misclassified. This basically comes from the gradient descent criteria. This is your expression for the weight updation. You keep on doing this unless you are correctly classifying all the samples. You keep on updating, and this eta is your learning rate. Now this is basically the perceptron algorithm. Now there is one more thing, you can do these updates sequentially, which is called the sequential form of the perceptron algorithm. There what you do is, in case of sequential algorithm, you simply, what should I write? In case of sequential, you take one sample at a time and you update the weight vector just based on one sample at a time. So eta xk in case if xk is misclassified. So you have an initial guess of W and you take one sample, you try to classify it, try to compute W transpose X. If it is wrongly classified, that is your W transpose X is less than 0, you add eta times Wk to your weight vector. Now you move on to your next sample, try to classify that. If it is misclassified, again you do this addition, and you keep on doing this unless you are at some value of W with which you try to classify all the samples and none of them are misclassified now. At that point you stop. So this is basically the sequential version. So in the original version, you took one weight vector, you classified all samples, selected the misclassified ones, summed them up, added to the weight vector. In case of sequential update, you do not take all of them together. You take one sample at a time, you try to see whether that is misclassified or not, and you update based on that. So as I have explained, so the idea for this sequential update idea, it helps in reducing the memory usage. So when you are just needed to have one sample at a time, you don't need to store all the samples that you have. and select from them and add all of them together and get the weight updation. You can just load one sample, check that, update your weight vector, take next one. So the amount of memory space required is much less. So in this perceptron criteria, as the it will not be much because you need to anyway compute, you need to classify all the samples anyway in both cases, whether you do sequential or you do overall update. But yeah, you need to update the weight more times, some sort of more computation time will be involved because of that, some more addition operations will happen. And also because you are just doing one sample at a time, the convergence might be slightly jittery, it may not be that smooth when you, as you have for the overall case. But the only benefit for which this is designed is it requires less memory space compared to taking all the samples together. So this is one version of the perceptron algorithm that is generally applied in practice, the sequential version. This is how we compute it. Now, given this, can anyone answer this? Which of the following statement is true for perceptron criteria? Convergence will be always guaranteed, or convergence will be guaranteed for linearly separable class, or both A and B, none of the above. Arun is saying B, Sunidhi, everyone is saying B. Yeah, right. B is the correct answer. Convergence is guaranteed for linearly separable classes in case of perceptron criteria. So given that, let us try to design one or two perceptron algorithm based classifiers. So this problem is based on that. So here you have a 2-class classification problem with 2D Boolean feature vectors. So your feature vector x is just x1, x2, and this x1, x2 are Boolean. So each xi can be either 0 or 1. Now consider two specific classification tasks as follows. In the first task, it is said that a feature vector x should be in class 1 if the integer represented by it is divisible by 2, otherwise it should be in class 2. So we can have 4 different feature vectors, since this is a 2D Boolean feature. These 4 feature vectors we can have. Now first one is 0, 0. So the integer it represents is 0, that is divisible by 2. So this will belong to class omega 1. I am denoting class 1 as omega 1. Next one 0, 1, that indicates the integer 1 which is not divisible by 2. So it should belong to class 2, that is omega 2. Next is 2, again this will be from class omega 1, and this is 3. So this is also not divisible, it will be from class omega 2. Now I will go to the other classifier later, but the question is, in each of these cases state whether the perceptron criteria is suitable for designing the classifier. So based on this we will have to say whether perceptron criteria is suitable for this or not. For that, what we should check, as we saw in the last question only, that perceptron algorithm will converge only in the case where the classes are linearly separable. That is the only case when this perceptron algorithm will converge, right. So what we have to check is whether these samples are linear, these classes are linearly separable or not. So in this case we can simply plot this and check out. Let us say this side is x1, this side is x2. First 0, 0, which is this origin point, this belongs to class omega 1. I am denoting this as a filled circle. Now 0, 1, x1 is 0, x2 is 1, that belongs to class omega 2, I am denoting by a cross. Now 1, 0 again belongs to class omega 1, and 1 1 belongs to class omega 2. Okay. So, these are the 4 points. So, you can easily see that if you draw a line somewhere in between these crosses and the circles, you can have a linear boundary that separates the two classes of points. So, these two classes are linearly separable. So, if we use perceptron algorithm, indeed that will converge for this set of data, this set of classes. So, yes, this is suitable for perceptron algorithm. Now, let us see the other example. Here it is said that a feature vector x should be in class 1 if it has odd number of ones in it, otherwise it should be in class 2. So, odd numbers of ones are there in these two. So, these two should be in class 1, other two should be in class 2. So, what do you think? Is perceptron criteria suitable for this? Sunidhi and Arun, you are saying no. Yes, you are absolutely correct. So, let us check if these are linearly separable by plotting this again. x1, x2, 0, 0 belongs to class omega 2, 0, 1 belongs to class omega 1, 1, 0 belongs to class omega 1 and 1, 1 class belongs to class omega 2. So, the diagonally opposite elements are belonging to the same class. So, no way you can draw a straight line to separate the two classes. So, these two classes are not linearly separable. So, your perceptron algorithm will never converge for these two classes. So, it is not suitable for a perceptron algorithm. I hope the idea is clear. You just need to check whether the two classes are linearly separable or not to decide whether you should go for a perceptron based classifier or not. Now, given that the last part of the question says if the perceptron criteria is suitable, then derive the classifier using the perceptron algorithm. So, let us do one example, one exercise of how this perceptron algorithm goes to get the complete idea, to derive the classifier. So, here it was suitable for the first example, where 0 0 and 1 0 were belonging to the same class and 0 1 and 1 1 are belonging to the other class. So, from class omega 1 we have from class omega 2 we have 0 1 and 1 1. So, the first step will be to augment the feature vectors, that is you append 1 to each of the feature vectors. You augmented. Now, what you have to do for the class omega 2, you have to negate all the feature vectors. So, these two will become this. Now, you start with a initial guess of W, let us say W0, which we take as all zeros. All zeros. So, what we have to check, we will go with the traditional algorithm where we consider all the samples together, not the sequential one. So, what we have to do is, we will use this W and we will try to classify all the samples. And so, if the classification is correct, what should be the condition? That your W transpose X should be greater than 0 if you have correctly classified it. So, You see, since W is 0, W transpose X for all these samples will be 0. So, none of them will be positive. So, all are misclassified. So, how will you update your W1? You will do W0 plus eta times summation of the X case. Here all K you will have to consider, because when you have W0 all zeros, none of W transpose X is greater than 0. So, you have 0 0 0 plus eta, let us say we take eta equal to 0.1 and sum of all of these. So, you have 0 minus 2 0. So, your first update of the weight vector becomes this. So, after iteration 1, this is your updated weight vector. Now, again what you have to do is, again you will take this updated weight vector and try to classify all the samples. You will compute W transpose X, check if it is greater than 0 or not. So, for the first sample it will be 0, the second sample also will be 0. So, both are not greater than 0. Then for the third and fourth sample you will have 0.2, W transpose X will be 0.2. So, for this case it is 0, this case it is 0, this case it will be 0.2, this case it will be 0.2, right. So, these two samples are correctly classified, these two are not. So, in the next iteration of W, what you will do is W1 plus 0.1 times summation of these two feature vectors. Let us say the first two feature vectors you will sum up. So, you will get 102. That is, you are getting 0.1 minus 0.2, 0.2. This is your new update. Now, let us see what happens if you try to do the classification. How Arun, when computing W1, how X is 0 minus 2 0. Okay, I will tell you once more. So, at the starting we had W0 all zeros, we assumed. It can be any arbitrary initialization, we started with all 0. So, first step what you need to do is, you have to check W transpose X for all the samples, these all 4 samples, and that should be greater than 0. So, in this case all of those will be 0, none of them will go to greater than 0, all are on the decision boundary. So, what we will consider, that all 4 of these are misclassified. So, how do you update? This is your update equation. Here you sum up only those X k's which are misclassified, which are missed. So, here all 4 are missed. You just sum up all these 4 feature vectors. What you get is 0 minus 2 0. That is how we ended up with 0 minus 2 0. Is that clear to you, Arun? Oh, fine. Similarly, you do the next iteration. Now, our updated one is 0.1 minus 0.2, 0.2. You can again check with that. So, what happens if you have 0 0 1, it will be 0.2. So, which is positive, W transpose X is positive. So, it is correctly classified. For 101, 101.3, this is also correctly classified. Now, if you take from class omega 2, 0 minus 1 minus 1, here W transpose X will be 0.2 minus 0.2, 0. So, this is not correctly classified with this W. So, earlier iteration it was correctly classified, now you did some update, it is now wrongly classified. And for the last one, minus 1 minus 1 minus 1, here what will happen? this is also less than 0, right. Minus 0.1 plus 0.2 minus 0.2. Yeah. This is also wrongly classified. So again you will have to do the update, but this time you will just add these two samples. Like that you will have to keep on doing the iterations until you are being able to correctly classify all the 4 samples. That is, W transpose X is positive for all the 4 samples. If you go for 2 more iterations, the final W that you will get will be 0.1 minus 0.4, 0.2. You can simply try to do a few more iterations. So every time you try to classify all the samples with your current estimate of W, and whichever are not giving W transpose X greater than 0, you will have to consider those as missed ones, and you add those up and add to the current estimate of weight vector to get the new estimate of the weight vector. Now here we choose the eta value as 0.1. So this choice is critical. If you put eta value too low, it will take much time to reach at your convergence. But if you put eta value much higher, then it can jump over the required solution, required minima, and it can keep on oscillating. You may never get to the actual scenario. So for this example, we randomly took this one. In gradient descent, they do minus eta. Do you mean minus eta, Arun? That will just a minute, let me check. So it's basically your gradient descent formula is that you will have to move opposite to your delta j. If your loss function is j, you will compute the gradient of j and you will have to move to the opposite of that gradient to get to your solution. So you can Arun, you can again go through the lecture video of how this in this case is coming as plus eta. So I can give you a brief explanation. So here what we want is W transpose X should be greater than 0. So whenever W transpose X is less than 0, we form the loss function J as J of W is equal to summation of minus W transpose X for all X which are misclassified. Okay. So whenever you have misclassified X, W transpose X will be negative. So you negate that, you get a positive quantity. So your loss function is positive always when you have some misclassified samples. When you have all correctly classified, this is 0. Now if you take the gradient of this, it simply becomes minus summation of X for all X which are missed. Now your gradient descent formula wise, Wk plus 1 should be Wk minus eta times delta j. So whatever is the direction of your delta j, so if this is your loss function plot, so let us say at this point your gradient is towards this side. So if you want to reach the minima, you should go opposite to the gradient. That is why Wk minus eta times delta j, but in this case your delta j itself is minus summation of X. So that only reduces it to plus. That is how you get the plus here. Pooja saying how you get value of w.1. So actually Pooja, you need to do 2 more iterations with this w. So now you have so now you have this value after iteration 2, 0.1 minus 0.2, 0.2. If you do once more, this time you will have to add these 2 samples only. So if you add those, what you will get is 0 minus 0.40. With that again you classify and again you do the update, you get this correct 0.1 minus 0.4 minus 2. You can just check it out and let me know if this is not coming. I may have some issues. Okay. So last one check we should do. So I am saying that w should be 0.1 minus 0.4, 0.2. So with this w, we should get w transpose x positive for all the samples belonging to class omega 1 and negative for all the samples belonging to class omega 0. So in our case, omega 1 samples were 0, 0 and 1, 0, right? 0, 0 and 1, 0. You have to augment by 1. So if you compute w transpose x for let us say this one, you get 0.2 which is positive. So you will classify to class omega 1. And for this one you get 0.1 plus 0.2 which is 0.3, again positive, you will classify to class omega 1. And for omega 2 samples you should get w transpose x less than 0. Samples are 1, 0, append 1 and 1, 1, append 1. So if you compute this for the first one, your w transpose x will be this is not 1, 0, this is 0, 1, right? 0, 1 and 1, 1, right? Zero, 1, 1. So if you have 0, 1, 1, then w transpose x will be minus 0.4 plus 0.2. So minus 0.2 which is negative, so it will belong to class omega 2. And all ones, then your w transpose x will be minus 0.1, again negative, so it will belong to class omega 2. So the w value that we got is actually correctly classifying both samples from both the classes. So this is a correct convergence that we have achieved. So with this I'll stop for today. So these were the all problems I wanted to solve, but I'll be available for half an hour more. If any of you have any question, we can discuss that now. If I don't negate feature vectors of omega 2 and then I use the formula omega naught minus no. So if you don't negate the feature vectors of class omega 2, then what will happen? For class omega 1 you have positive value of w transpose x, and for omega 2 you have negative value of w transpose x. So whenever you are misclassifying, that means if it is from class omega 1 and it is w transpose x is negative, then it is a error. when it is from omega 2 W transpose X is positive, then it is a error. So, if you want if you want to form a loss function out of it, then you will have to negate those of 1 classes to make the overall loss function positive. So, otherwise your if you are taking W transpose X as loss and you have not negated any of the classes, then for 1 class that quantity will be negative. So, you will be adding negative to the overall loss J. So, that should not be the case. You should always, the loss should be positive quantity. That is why when you reach the minima or when you have all correctly classified, your loss value should go to 0. Otherwise, it should be some positive loss. So, from both classes, if you want to add the misclassified one, that should be positive. Otherwise, you are adding positive from one class, negative from one class, that will cancel out. Am I making sense in what I am saying, Arun? Yeah, okay. So, any of the 2 classes you will have to negate. You can add the loss without the sign symbol. Yeah, that is the same as negating, right? So, when you are just not putting minus W transpose, whenever your W transpose X is negative, you are not putting that sign. That means you are actually multiplying it with the sign. And also you should have a like uniform criteria for both the classes, right? If you are not writing it with sign, that means okay, so you want to say you want to take the modulus, but if you take modulus, okay, I mean that is not the perceptron algorithm, that is not how it does, but if you take no, so that will also not let me think. So you have to compute the derivative of mod, right? So your mod of, let us say mod of x function is something like this, right? Just a minute, Sri Vidya, you are saying if you negate both the classes will give positive value, then how will you classify? So, you will negate during the training point only. This is just to have an algorithm, suitable algorithm for training. You will negate one of the classes, you will make both positive, then you do not need to check for positive negative. Always you have a positive value, you are correctly classifying that sample. So, whenever you have negative value, only those you will consider as misclassification. But when you go for testing one sample, obviously you will not negate that sample. You will just do W transpose X with the original value, and if it is positive, you will classify to omega 1. If not, you will classify to omega 2. This negating is for getting to the optimum W value. Pooja, these PPT presentations will also be available along with the recordings. Yeah, let us go back to Arun's question. So, if you have mod, the function is something like this, right? So, in positive side of x, your derivative will be positive, but in the negative side your derivative will be negative. So, it will not always be minus eta of loss, your derivative is changing depending on you have the positive, you are on the positive side or negative side. Yes, sure, Arun. You can just pick up.
Yeah, so for omega 1, if it is greater than 0, it is correct, so no loss.
Yeah,
For omega 2, if it is less than 0, there's no loss.
yeah.
So if I group whichever fails omega 1 criteria and whichever fails omega 2 criteria, if I put all of them as delta J,
Yeah.
then it becomes absolute loss.
So you mean to say your J of W will be summation of mod of W transpose X, right? Sorry. This, right?
Yeah.
Yeah.
So then in that case, I can use this W of k plus 1 is equal to W of k minus eta delta J directly.
No, but here also you need to compute, when you compute the delta J, it will not always be positive, right? Depending on your X is positive or negative, your delta will be either positive or negative. So mod function, if you are taking, mod is not always same derivative.
No, say loss is either 0 or positive only, right? Loss
Yeah,
is,
loss is positive, but if you are derivating it here with respect to W, right, your loss is always positive. That's why I drew this as this curve. The mod is always be positive, y axis is always positive, but you are derivating with respect to W, so that can be positive or negative. Are you getting my point?
no, I got it because in other approach like linear classifiers,
Yeah.
we use the gradient descent algorithm is the learning rate of the loss factor. So, I mean,
So you have to see what that loss function is. I guess it's something else. So that the derivative only comes as positive. It's not mod. If you take mod, the derivative won't be always positive.
now same here is a classification problem. Suppose if it is a regression problem. So I mean, I'm coming from the regression background.
Yeah.
We're not classifying, but we are regressing a particular value. I'm predicting a
Huh.
value.
Huh. Yeah.
So there when we look for the optimization,
Like
so
mean absolute error you want to
yeah,
reduce. Right?
so
Yeah.
so the time we always start with random values and then we compute the loss. Then the next weightage W will be the random generated value minus learning rate of the loss. So we always take the minus as the, so we go, that's why it's called descent minus. So I was saying but it will not be descent, right? That's why I say.
So descent basically comes because you are from in the loss. What do you say? Uh, Loss surface. You are descending towards the minima. That's why the descent. Your gradient is, you are taking the direction of the gradient and you are descending towards the minima.
Okay.
From there it comes. But yeah, the question that you were saying, if for regression you take W transpose X, you compute the error, that's correct. Y minus W transpose X you will compute, and you take the absolute value of that and you try to minimize that.
Yeah, compare with the true value.
Huh.
So whatever is the difference is the
So
loss.
for example, Y minus W transpose X,
Yeah.
the absolute value of this, you
Yeah.
take the sum and you try to minimize this.
Yeah. You accumulate the loss for all the samples.
Yeah, right.
So that way, then when you want to find the next optimal value, it will be previous one minus the learning rate of the accumulated loss.
So this is your J. You want to, so you are saying your next W, let's say W dash I write, That will be W minus eta times J, you are saying?
Yeah, delta J.
Delta J, right? When you compute delta J, then it may not come as always positive quantity, right? Depending on so when you do this derivative with respect to W, so depending on whether this y minus w transpose x is positive side, negative side, this modulus derivative can be different, because when you go for this particular solution, the final solution that you get, it's w is the median.
Okay.
Yeah, you can just try to do the derivative of J and check out what is happening. Derivative with respect to W.
Okay. Thank you.
Any other question from anyone? So I will keep this session open till 6 as we have instructed. If you have any question, you can ask that, otherwise you can leave the meeting also, because I will not solve new problems, I will just discuss whatever doubts you have.
So can I ask a question from the previous assignment, which is already scored already?
Yeah, sure.
So there was one question in the previous assignment, which was how many discriminant functions minimum you will need for solving a four-class problem.
Yeah.
So the answer was four, but I thought it is three because when it is binary, you can solve it with one, right? Any class problem, then you're able to solve with one discriminant function.
Discriminant function is not one. So so for each class, let's assume the minimum error based classifier. So you need to, if you have two class, you need to compute the class posterior probability. If it is greater than 0, if whichever class is higher, you put it in that class, right? So you compute that quantity for both the classes. So in this case, we can consider that as your discriminant function. So discriminant function, you compute some function quantity for each of the classes, and you take whichever class has the maximum value, you take that as your final class. So
Correct.
when you are going for the one you are saying that you can do from one only, that is basically the decision surface. So you have two discriminant functions, g1x, g2x, you compute g1x minus g2x, you get one decision surface. From that you can just take whether it is positive, you can assign to one class, negative in other class, just one function will do. But when you are talking about discriminant functions, you have two of them. How the whatever is the number of classes, you have that many discriminant functions, you take the maximum.
Like the more of thing, the reading the language, I think. Okay, I got it. Because as I said, function is one, but you compute for the two classes, right?
Yeah, the function, function is not one, the structure of the function is same for both all the classes. So for example, in these normally distributed classes that we talked about, the mu1 sigma 1 value, mu sigma values will be different for different classes, but the overall structure is the same. GIX is the general structure, but from that you put different values for different classes and get g1x, g2x, g3x. Does that what you are asking about?
Yeah, so if it is a binary classification, you would draw only one decision boundary, right?
Decision boundary is one.
Only one. Now, if suppose I have one more class, that means I have three classes now, then I draw two decision boundary.
Yeah, right.
So
Decision
when I have
boundary is
four
one
classes-
minus.
Yeah, exactly. So, I mean, the way the question was asked, I thought it was more of how many decision boundaries you need.
Okay.
So it was like discrimination function was, okay, class minus one. Okay.
Yeah. Decision boundary is n minus 1, but discriminant function will be n for n classes.
Similarly, I mean, if nobody has any questions, I keep going, even as please actually. In the previous week one assignment, there was question number 6. It says, suppose the Fourier descriptor of a shape has k coefficients, and we remove the last few coefficients and use only the top m. Now, with that, you try to reconstruct the original shape, right? So there were 4 choices given. In that, the correct answer given by your group is, we will get a smooth boundary version of the shape. I'm not sure how we can get it if you are dropping m minus k coefficients. You will not exactly get the original smooth boundary version of the shape, right?
No, the original version you will not get. So when you do a Fourier descriptor, the lower order coefficients, those are for low frequency, right, and higher order coefficients are for the higher frequency component, right? So you are dropping some of the high frequency coefficients. Just me just share my screen once more. Yeah. So let's say you have some function like this, something like this, and you got the Fourier coefficients for this. So the lower order coefficients, which are for the low frequency part, that will capture the low frequency content of this signal. So low frequency content is kind of the overall flow that is going on, something like this, and the high frequency content will be this thing that is on top of the overall shape. So when you drop the higher order coefficients, those are basically the high frequency components. You are dropping the high frequency one. So this jittery thing, this thing you will lose, but you have the lower part. So this lower this thing, kind of low pass filtered nature of the signal, that we will be able to reconstruct. You will lose these details out of it. Does that make sense to you?
Yeah, I got it. Okay. What's the difference between a signature descriptor and polygonal descriptor? That was one of the question there. Polygonal descriptor and signature descriptor.
So is this also answer published?
Yeah, it's published one.
Can you tell me the options? I don't remember the question actually.
I don't know if I can share my screen or.
Yeah, you can, I guess.
Or the options were, yeah. The question was the plot of distance of the. Okay, let me share the screen. Otherwise, okay. If you don't mind.
Yeah, sure.
This one.
The plot of distance of the different boundary point from the centroid of the shape taken at various direction is known as. So what do you think the answer is for this?
No, I mean, my answer is wrong, but I was trying to understand. The correct answer as per the examiner is A, signature descriptor.
Yeah, right. So
okay.
So this is how signature descriptor is defined. You take the centroid, you take the distance of all the boundary points, you plot. So something like you have a shape like this. This is your centroid. This is some reference direction you are taking.
Now, sorry, I stopped sharing. You have to share again. Sorry.
My screen is already shared. You can just pin my screen, I guess.
So since I was sharing, it might have overwritten your sharing. So I'm saying.
Oh, is it?
Yeah.
Okay. Just
So
let
share
me
again.
share again. You can see it, right?
Yes, ma'am.
Yeah, we can see. We can see.
So if this is some kind of a object, you take the centroid, you take a reference direction. Now from each boundary point you compute the distance between the boundary point and the centroid, and this angle you compute each time. You plot that angle and the distance. This is what your signature descriptor definition is. This is how you define a signature descriptor. But when you want to do a polygonal approximation, that is basically you are trying to approximate the boundary of the shape by a polygon. Now based on top of that polygon, again you can compute that feature descriptor, this signature descriptor. So first let's say you have this shape, you want first the polygonal approximation. For that you take two farthest points on the boundary, you join the points, that is you are dividing the boundary in two halves. Now let us first consider this half. From all points you take the perpendicular distance to this line, and whichever point has the maximum perpendicular distance, let us say this point has, you take that as the next vertex and you join these two, and you keep on doing this unless all these distances are below a threshold. So by doing this, what you will finally get it, let us say this was the object, something like this, you get a shape maybe like this. This is what your polygonal approximation is. That's some arbitrary boundary that you are approximating by a polygon. Now you can again compute signature descriptor on top of this polygon.
Okay, got it.
Yeah.
Thank you.
Okay, so in case none of you has any question, should we stop the session for today? We will meet again in the next week. So just to let you know, next week I will not be taking this session on Saturday. Instead of that, I will take on next Monday. So instead of 18th, I will take it on 20th at the same time. You will get mails accordingly from the NPTEL team. Okay. Thank you guys for joining. We'll meet again in the next week.